I spent years obsessing about cars, either driving them, reading about them, or watching folks who drive them to the limits on a racetrack. And I get how they work. When you press down on that accelerator or twist the throttle on a bike, inside the engine, the fuel is combusting, exploding so to speak, and that is pushing the piston up and down. And all that energy and force is transferred down to the shaft, to the wheel turning. But how does a rocket engine work? And why does it look the way it does? Let's find out. To understand this, I've got two really smart engineers from Skyroot to spend their Saturday morning explaining rocket engines to me. Hey Rohit. Hey Divya. Shall we begin? Yeah. All right. So Rohit, why does the rocket engine look so different from a car seat?
Yeah, in a typical car engine, what you're trying to do is translating the chemical energy, which is stored in the fuel, to a mechanical energy. You are trying to roll on the surface of the earth, right? So that's what car engines do. But in rocket engines, you need to go to space. So what we do is that we try to generate all of the thrust which is required for the rockets by shooting gases at incredible velocities, so that you generate the force which is necessary for you to go to space.
Okay, so if I had to accelerate a rocket, I essentially eject that mass at a higher velocity?
Yeah. We use something called a nozzle, a Laval nozzle, by which we can reach to speeds of 3 to 4 kilometers per second by the time the gases exit the nozzle, which generates the thrust.
3 to 4 kilometers per second.
So to give you the context, it's like covering from Kashmir to Kanyakumari in less than 15 minutes.
So if I were used to a rocket, I can do Kashmir to Kanyakumari in 15 minutes.
Yeah, less than that.
So what I get from you all is that shape, what you said as a Laval nozzle, it has a purpose to it, and that is why perhaps rocket engine looks so unique.
Okay, let me explain in detail. Yeah. The shape of the nozzle may not be totally intuitive, so we need to resort to math in order to understand why it is so. Okay, but what it says is this: if the Mach number is less than 1, so that is the ratio of velocity of the flow to the speed of sound. Okay, so if the Mach number is less than 1, the area has to reduce in order to flow to accelerate. Okay.
So that's the convergent part. So basically the gases are moving into a lower area and ejecting at a higher velocity. The same applies in garden hose also. So the water is entering into a lower area and ejecting at a higher velocity.
Yeah. So, but when the Mach number is greater than 1, that is when the flow is actually moving at higher than the speed of sound.
Just a doubt. So the gases enter from the left and then you are converging it, and therefore it increases speed.
Yes.
Okay.
Yeah. So in the case when Mach number is greater than 1, the area has to increase in order to accelerate the flow. Okay. So you can see the shape of the nozzle form. What we do is actually we join these two. The gases enter from the left. As it moves through the nozzle, it continuously accelerates and reaches very high speeds by the time it exits nozzle.
But why does it, when the Mach is greater than 1, why do the area has to expand for it to accelerate?
So that's where the math helps. You can quickly look at an equation as well. So in this equation, V is velocity, M is Mach number, and this is area. Okay. What this says is, if you want to accelerate the velocity for Mach less than 1, this is a negative term. The area has to decrease.
That's
So
the
that's
one on the left where you have.
Yes, this is the convergent portion, right? But if it's greater than 1, if you want to increase the velocity, the area has to increase. So, as you can imagine, this is where the transition happens. And this is the location where the flow will become supersonic.
So what I understand is gas is coming from the left, you reduce the area, you converge it, it accelerates, and by the time it reaches the throat, it gets a speed of sound, then that based on equation it flips, and you expand it and continues to expand.
Yes.
Accelerate.
So that's exactly what we do as well. So what we do is that, so this is what we call a combustion chamber in a rocket. So this is the zone where we burn our propellants. and then push all of those gases through the nozzle and accelerate them and they exit at a very high velocities.
So you don't need a piston. So it's the shape of this convergent float and divergent that's accelerating the.
Yes. There are other components in the engine where there are moving parts like pumps, valves, and all of it. But the function of all of them is to actually feed the propellants the required flow rates so that they burn here and then they flow through the nozzle to eject and generate the thrust.
So that convergent, float, and divergent together was called the T-Laval nozzle.
Okay, T-Laval. I'm assuming it's named after someone?
Yes, Gustav from T-Laval. So he's basically a steam turbine engineer. But this concept can be used even in rockets also, like any compressible fluids.
For
Design.
steam fluid also this like squeeze it and then accelerate. That same principle is adopted for rocket engines.
It's for any gas.
Okay.
Works the same.
Oh, so this shape, that's why the rocket engine looks like a unique conical shape because of this T-Laval nozzle.
Yes.
So, do all nozzles look the same?
No, nozzles come in different shapes. Okay, majorly there are conical, bell, altitude compensating nozzles. Okay, conical nozzle is one of the most simplest type of nozzle. It's simply a simple cone. In this nozzle, what happens is that all of the flow is not exiting along the axis. Okay, so you can see there will be some flow which is directed in a different direction. So which is not very optimal. Okay, so that's where the bell nozzles come in. So these are all carefully shaped nozzles, which ensures that most of the flow exits along the axis. You can clearly see that in the bell nozzle, the performance will be much superior compared to the conical nozzle.
The opposite force that.
Yes. Yeah. Force will be in this direction. Okay. So, but conical nozzles are relatively easier to manufacture. So engineers decide what to go with depending upon their application, their requirement, and the performance requirement, right? And then there's another category called the altitude compensating nozzles. What we need to understand is this. So from the combustion chamber, as the flow flows along the nozzle, the pressure continuously decreases. Okay, so we try to actually increase the velocity as much as possible. Okay, so what happens is that the pressure within the nozzle actually decreases up to almost 0.2 to 0.3 times of the ambient pressure which is surrounding us. So in that case, what happens is this: the external pressure which is acting on the nozzle actually generates kind of a negative thrust. Okay, so in order to compensate for this, the altitude compensating nozzles are designed such that the flow automatically adjusts as the external pressure changes. And also, what is worth noting is this: as the rocket keeps climbing up, the surrounding pressure continuously decreases.
Okay. So atmospheric pressure drops.
Yeah, atmospheric pressure drops. So for this bell type of nozzle, you can imagine that the thrust what is generated for the same nozzle at sea level will be lower than compared to what it is generated at vacuum conditions. Okay, but aerospike nozzles, one of the type under altitude compensating nozzles, can generate better thrust at sea level than a bell nozzles.
But the plume is adjusting.
Yes, but these are not generally used because these are heavy, but more complex to design as well, because the throat portion, which is most complex, which has highest heat flux of a nozzle, is actually increased in size. So the engineering becomes more difficult. The size of the engine also becomes more difficult. So most of the time you see only the conical or bell nozzles used extensively in most of the rockets. Which may be interesting for you to know is this: one of the most common type of bell nozzle is something called a Rauch bell or a Rauch nozzle. Okay, he's an Indian engineer, did much of his pioneering work in USA. So he has come up with the most optimum nozzle where you can maximize its performance while keeping its mass as low as possible.
Oh, is it a recent nozzle or was this developed?
Oh, it's developed way back in 1950s.
Oh,
but it is still used very extensively by many engineers for their
it's Indian rocket scientists who developed this pioneering work in 50s in the US.
Yes.
Still continue to use.
Yes.
Yeah. Oh, that's amazing.
Yeah. There are any other questions?
Yeah, we do have some thoughts. So I know there are different types of rocket fuel. So does the choice of rocket fuel impact the choice of shape of a nozzle?
The answer is no. All these fuels, once they come into the combustion chamber, you're essentially burning them and converting them to gases. So for gas flows, it doesn't have any implication on how you choose or how the nozzle shape.
So in region cooling, right? Does nozzle also have region cooling, and is it run across the length of the nozzle?
It's not required to have region cooling throughout the length of the nozzle. So what happens is this. So as you move along the length of the nozzle, the throat portion is where you have maximum heat flux. Okay, so that portion you can use region cooling along with about a bit of film cooling as well. But as you keep exiting towards the divergent, the heat flux what the nozzle wall faces continuously come down. So after a particular point, we can actually go for materials which can actually withstand high temperatures. You would want to have that transition because if you go for that radiative cooling is what we call them, the realization is simpler. You don't have to have all these coolant channels, and the weight is also higher.
Can we use different materials for whole nozzle, like this part we use?
Yes. See, in rockets, copper is used very extensively. Inconels are used very extensively, and for radiative cooling, you use materials like stellite, columbium, or even inconel for that matter as well. We use coppers typically in the rocket nozzles because they have very high conductivity. Okay, that helps, especially near the throat portion where the heat fluxes are very high. You want materials which are which conduct a lot of heat. Okay.
I want to go back to one of the conversation you had when you were explaining convergence and divergence. You said when it's above m is above 1, the mark is above greater than speed of sound, you expand to create greater velocity. Now, does that mean I continue to expand, I increase the length of the nozzle, I get higher and higher and higher velocity?
What happens as you keep increasing the size of the nozzle? Okay, in our terms we call something called we speak in terms of area ratio. Area ratio is something, if you take a nozzle, you cut at any particular section, what is the area, okay, compared to that of the throat area. It's a ratio of that. Okay, so if you keep increasing the area ratio, you can definitely increase the velocity. Okay, but you're also adding to the weight of the whole nozzle. Now, this can be looked in two aspects. Okay, consider a rocket which is operating in sea level. Okay, what happens as we keep increasing the area ratio is that the pressure in the nozzle also continuously drops. We have seen
inside the nozzle.
Yes, inside the nozzle. Okay, so after a particular point, what happens is that the flow stops attaching to the nozzle and separates. Okay, so that causes issues with respect to side loads and so on and so forth, which is not even adding to the performance of the nozzle. So you don't want to simply add it. But an engine which is operating in vacuum, you can theoretically do that. But again, you're optimizing with respect to the weight of the engine. It's not just not the weight of the engine as well. As you keep increasing the engine length, right, you're also adding structural mass to the whole launch vehicle. So the rocket itself becomes longer. So that's a trade-off of what we can do. At a particular point, we'll notice that by adding that extra length is not adding to the overall payload. See, for a rocket, we are only trying to maximize the payload at any given point. So as you keep increasing the length, the structural mass goes up, which may translate to loss in payload. So there will be a very nice, perfect, optimum point where you want to say, hey, this is enough, and
so all of that shape is to find the right balance and the right performance required for the mission.
Yes, the length of it.
All of this what we discussed is on the what happens after the fuel is combustion and how the hot gas is injected. So what happens before the combustion chamber? What are the things that is considered while designing an engine?
So there are different architectures in which you can actually feed the propellants to the combustion chamber, like pump-fed and pressure-fed engines. We can deep dive more about them in the future episodes of Flow State.
So that was episode 2, where I learned rocket nozzles come in different shapes, all for a purpose. And this is Flow State, a free-flowing conversation on rocket science and more, where we dig into ideas and innovations powering Skyroot.